like this, there's 8 bytes here, and then there's n bytes here. When we're all done, what it returns is a pointer not to the beginning of that allocation, but to 8 bytes offset from the beginning. And this is where we store the reference. So we say x equals that. Then we can say casting x into an int star equal 1. What does that mean? Say no. Yeah.
Are you setting the reference?
You're setting the reference count to 1, exactly. So that puts a 1 in here. So x is that. If I want this to be an integer, what I'm going to do is pass that pointer into an int star. Oops. That's why you were wondering. And then you reference it. So that's good. Yeah. Right. Sorry. And that puts a 1 in it. And then you would return x plus, x minus 8. Does that make sense? Yeah.
So we initialize the malloc returns a void star here, right? So the whole block is void star. That's not cast the.
Yeah, so we're going to talk more about what void star means later in the course. You're right, it is a void star. A void star is a pointer to a type you don't know what it is or you don't care. Void star pointers can't be dereferenced directly. So when you malloc something, the allocator doesn't know the type of the left-hand side. So malloc and also RC malloc return a void star. Void stars you can add and subtract to them as if they're char stars. So this actually adds 8 to the address. But you can't dereference them, which is why I did the pass here. This P is also going to have a type. It might be struct X star or something like this, or maybe an array of integers. And this assignment is an implicit cast. It converts it to a void star. Other questions? Okay, you're going to use a technique like this, similar to this week. When you implement malloc, you're going to implement a very simple malloc tree, simple heap. And one of the things you have to do when you allocate objects in this simple heap is the same as in the real malloc, real heap. You have to keep track of the size of the object. And so you're going to do that. This is not reference count. This is what you're doing this week with malloc. You're going to do that by doing this kind of thing, including the size right here. So that when you say 3, you know how big the allocation was. So you get some chance to experiment with this. Feel free to use this code as a guide. That's what we're expecting.
Is it only 8 bytes for 64-bit or something?
No, so this is the last thing I wanted to say about this. Is why is it 8? Because an int is how many bytes? On every machine, an int is 4 bytes. So what's going on here? Why do I have, I've got 4 bytes here. I'm just expand this all out. I've got 4 bytes for the ref count. Then I have 4 more bytes. And then I have what the program asks for. What's the purpose of those second 4 bytes? Why is it 8, not 4? Because of alignment. So when you say malloc, the allocator doesn't, as I just said, doesn't know the type of what you're asking for, what you're going to put there. So it doesn't know what kind of alignment constraints you're going to need. If this was an array of longs, for example, or a struct that had a long in it, then that needs to be allocated to an 8-byte map. If, on the other hand, it's an array of ints, it will only be 4 bytes. But the allocator doesn't know that. So malloc, one of the constraints on malloc is it always returns, the address it returns is always aligned to the biggest thing, which is 8. plus 8. Also right. Any other questions? Okay, so we looked last time at one example. Now we have another example. So this is on Piazza. You need to go get this file under the tab code using class. There's a zip file, extract the zip file, and get this file in an editor. And then what we're going to do is add reference tracking to it. So this file, even though it's one file, it really, I want you to think about it, is consisting of 3 modules. So the first module has the methods create job and start job, and also I guess that's it. Create job and start job. And the idea here is to, well, it's just really a toy to get a reference counting example. But the idea here is that when you call, so create job just allocates an object, and it has a job number. When you start one of those jobs that you created, if you look just at the second half, the if J, is that sometimes it will start the job and sometimes it will skip it. And so the caller won't know, or shouldn't know, whether it started it or skipped it. Okay? If it starts it, what it does is stores that in a local variable. Okay? And it prints started. The next time you call start job, it finishes the last job if there was one. So if in the previous call you stored a job, now that pending job field points to a job, it finishes the job just by saying completed job, and sets it to null, and then does the next thing. In a separate module, we have these 2 procedures. One, organized job that creates a job and starts it, and then the final one, which is sort of cleans up at the end, is finish for the day, which starts the null job, just to finish a job if there is one pending. And then you call organized job with various different things. Remember, if they're divisible by 3, they're going to be skipped. So that one is skipped. And if divisible by 3, they're not skipped. So that one is skipped. That's not skipped. That's not skipped. That one's skipped. And each of them returns the data element of the job, which is just its number. And so we create it with that number. So if I run this, it will say skip job 1 because that job 1, the number is 7, it's not divisible by 3. Then it starts job 2, and then I start job 3, it completes job 2 and starts 3, completes 3 and it skips 4, starts 5 and completes 5. And then it prints out the total, which is the sum of all the numbers that weren't skipped. And that's what it's supposed to do, but it has a memory leak. It has a memory leak because it never calls free. Right? So there's a call to malloc, right there, and there's no call to free. And then the thing that needs to be freed is the job. And so I'm allocating jobs and I need to free them. And the problem is, I don't know where to free it. Because if the job is skipped, so first of all, I can't free it here, because I'm going to be accessing it here. So I create it here, I start the job, it has to still be alive after job returns. So the start job can't free it. Everybody see that? Does that make sense? So the freeing, if it's going to be anywhere, has to be down here. But the problem is once I get here, I don't know whether it saved it or not. And if it saved it, pending job still points to it, so I can't free it yet. But if it didn't save it, nothing points to it, so I have to free it. And this is the same as the MBUF example we looked at previously. This make sense? So, you now have the job of using reference counting to solve this problem. So the one thing I'll start you with here is that you have to call RC malloc instead of malloc. So now this job is a reference counted object, and it has a reference count of 1. So what I want you to do, first of all, is to find any place in the code where you need to call RC keep ref. And then after we do that, we'll come back to the free refs. It's a little bit more complicated. So any place in the code where you would need to do an RC keep ref, okay? We understand? Everybody have the code? I'll show it up here so that you don't have the code, you can kind of do it here, but it's much better to have this code in your own machine. If you didn't bring a machine, just make a friend. You don't have to do this individually, you can do it in small groups. It's on Piazza, under the tab Code Used in Class. It was loaded on Friday. Okay, let's take a pause here for just a second. How many places are you going to add an RC keep ref? Raise your hand if you think it's 0. 1. 2. Don't know yet. All right. Spoke too soon, sorry. Okay, let me try again. How many think they know? Oh dear. So, where do you call RC? Why do you do that? What is it you're looking for?
You're counting how many references are going to that specific variable.
Right, so we're counting the total number of references. When you call RC malloc, you get one. So we're looking for places where the number of references increases. So I create a new reference. And what would that look like in code?
An equal sign. So
Yeah, so it's either you have a pointer and then you have another pointer and you say this pointer equals that one. Or maybe you pass it as a parameter, because that's another way that you create a new reference. Maybe, those are the two. Okay. So if you trace through this code, we're looking at jobs. So we just trace through it. We start with create job, J equals create job. Do I need to do a keep ref there? There's an equal sign, but I don't do one there because create job is a procedure that's called RC malloc. And it returned to me this object already with the reference count of 1. You know, in a kind of way, it should go to 0 and then back up to 1 again, but as soon as it goes to 0, it'll be free. So when you're returning a pointer, just like what malloc does, you don't decrement the reference count because the caller gets a reference to it. You're giving yours up, but the caller's getting one, right? So at this point in the code, there's just one reference, and the reference count is 1, and that reference is the variable J. Okay. And then I call start job. So now in start job, we have the variable J, this is the pointer. Is there any place in this code where there's a variable assigned to J? Pending job equals J. So when that line of code executes, after it executes, how many pointers are there to the object? 2. So that suggests that we need to add an RC graph right here. And it could be either pending job or J, they're equal to each other, it doesn't matter. Now, is there any place else? Yeah.
We only have to add it once with this.
Well, I don't know. What do you think? First one is you only have to add it once. Why do you ask that question?
I was curious because we have like technically 2 references to the same object.
We have 2 references, that's right, J and pending job, and after, when we get to this line of code, what's the reference count of that object? 2. And that's what we want, right? Does that make sense?
Yeah.
Is there any place else we need to add keep ref? Who says no? Who's not sure? Who says yes? Why do you say yes?
Like the scope of organized job, is that variable whatever's returned from the base job?
Got it. So right here, what's the reference count there?
3, I guess. Or, no, wait.
Just after the call to create job.
There's 2 there.
No. Before you call start job, create job is right here. RC malloc. What's it right there?
1.
1. Nothing changes, right? So when I get here, it's still 1. And that's correct, because at this point, the only thing that points to it is J.
Is it because the pointer in the first method goes out?
Yeah, exactly. Is create job had a pointer, but create job returned. This is a local variable. That variable's gone. That J is gone. So now I only have this J to worry about. And that's the way it'll always be. If you return a pointer, you don't increment the reference count because you just passed the reference. Old one went away. This is a return statement. That reference is gone, and now you have it. Any place else you think we should add one? Yeah.
I have a different question.
Yeah.
What if you call create job but didn't assign any variable to the result? Then would you call RC3 and create job?
If you call create job, yeah, we're going to come to that. So the question is, do we need a free ref somewhere, right? That's what you're asking, and I'm going to come to that in just a second. But let's deal with the keep refs first. Any other keep refs? No. So to figure out where the keep refs are, I mean, you only have a keep ref if you save an extra reference. Okay? So a lot of times you're just passing this around. You're not saving an extra reference. You don't have to do anything. Now, free ref. So we're gonna look at this procedure and then this procedure. Both of them maybe have to have a free ref. So just first looking at start job. Any place we need to do a free ref. I want you